Now we've reached the last part of this week's lecture. I hope you're still following. We're going to talk about balance laws or equilibrium equations. And here we talk about basically Newton's law, which means that under equilibrium, the sum of force over a body must equal to 0. So we look at the initial configuration. We have a body omega 0 with a boundary gamma 0, and we have body force density B0, and on the surface dA0 we have a normal N0 and surface force dF. In the current configuration, we have everything that is corresponding to the current configuration. The N and dA, omega, gamma, and dV and B, we have the same surface force. Then let's try to do a sum of force on both configurations. First, let's write the surface force dF in function of the respective stress tensors that we've defined in both configurations. On the left, we have the first Euler-Kirchhoff stress. On the right, we have our Euro-Cauchy stress. On the left, the sum of force would correspond to sum of the surface forces over this small area dA0 plus the sum of body forces equal to 0. On the right, we have sum of the surface forces over gamma, the boundary, and sum of the body forces over omega equals to 0. Now we can plug in this expression. We have P multiplied with N0 times dA0. And similarly, we can plug in the expression of tau, which is Cauchy stress tensor, multiplied with N and then dA. Now, whenever we have an integral over a boundary, all right, and then this integrand is something that multiplies with a normal of the boundary, we can use the so-called divergence theorem to transform this integral into a volume integral. So on the left, we would transform this surface integral into a volume integral with a divergence over P. Of course, this divergence would be taken with respect to the coordinates in the initial configuration, which is capital X. Similarly, we can use the divergence theorem to transform the surface integral into a volume integral, and divergence here will be taken with respect to the coordinates in the current configuration, which is small x. And because this is valid for arbitrary domain omega 0, we could take the full domain or just part of it. So the integral must be 0 in both cases, which means that this will be the so-called equilibrium equation for our body at each material point. This needs to be satisfied at each material point in the body. And similarly for this one. I believe this is already familiar to you. This is our equilibrium equation from undergraduate mechanics courses. And this is also the equilibrium equation that we used in linear finite element method. And this is the corresponding form in the initial configuration with the body force density in the initial configuration and first Euler-Kirchhoff stress tensor. The reason why we didn't use the second Euler-Kirchhoff stress tensor here is that the second Euler-Kirchhoff stress tensor multiplied with N0 will not give us any physical meaning of force, because that's the shadow or pullback force of dF. While here we are talking about force equilibrium, it has to be a physically defined force, which is dF. Okay, now we have the equilibrium equation, so-called strong form of it, and we would like to derive the principle of virtual work, or so-called weak form of it, so that we can then apply the finite element discretization. So we had the same procedure in linear finite element method. Now we are going to repeat it in the nonlinear or geometric nonlinear finite element method. So we start with the equilibrium equation, which is so-called strong form. This needs to be satisfied over the domain omega 0. The weak form of it basically says that if I consider this to be a residue, and the virtual work of this residue by a small variation of our displacement solution integrated over the domain omega 0 needs to be 0. They are equivalent, but the difference here is that now this is an integral equation and this is not. So you can mathematically prove the equivalence of the two. We are not going to do it. But just bear in mind, this contains actually more information than this one, because this one, when we say it, we also say that this needs to be satisfied in the domain omega 0, while here you can directly see this information. So what we're going to do next is to apply a series of mathematical manipulations to try to simplify this expression. We're going to use the fact that the variation of f, which is equals to variation of identity matrix plus the displacement gradient, equals to the partial derivative of variation of u with respect to capital X, because the identity matrix doesn't change, the variation rate is 0. Now we are going to apply the integration by parts to shift the partial derivative present in the divergence operation to the variation of u, and so that we are left with only p on the right. We can arrive at this expression. So when we shift the partial differentiation to variation of u, here we obtain the variation of f. On the right, after the integration by parts, we are left with only the p. And of course, we have after integration by parts, we also have a surface integral, which is shifted to the right. So the detailed proof of this equivalence can be found in an additional document that I've uploaded on Brightspace. This name of lecture 2 proofs. But after mathematical manipulation, we can arrive at so-called weak form or principle of virtual work in the initial configuration. This is the internal virtual work due to a variation of your displacement solution, or sort of a small perturbation to it. This is the external virtual work due to body force. This is the external virtual work done by the surface traction. And with this weak form, we can further modify it to bring out our Green-Lagrange strain tensor and second pure Kirchhoff stress tensor. The way to do is to focus on this term, express S as F inverse times P, which then we can express P as F times S. So we express P as F times S. Then we are going to make use of this formula, which is also proven in an additional document, lecture 2 proofs. Here, A would correspond to variation of F, B would correspond to F, and C would correspond to S. Then on the right, we simply plug in this expression, we would get what we obtain here. All right. Now, S is a symmetric matrix. When you have an inner product with a symmetric matrix, you are only actually multiplying the symmetric part on the left as well. So this is equal to this. And the symmetric part of F transpose variation of F is simply 1 over 2, the original form of the product, and the transpose of the two. And then you dot product with the S. So the inner product for second order tensor, which is matrix, you define like this. So let's look at the variation of the Green-Lagrange strain tensor. It takes a variation of this is the expression for E, and when we take variations, we apply it individually. So it's sort of like a differentiation, but not exactly the same. So we can obtain this expression for the variation of E. You can see that these two are the same. Then basically we arrive at the conclusion that the variation of F inner product with first pure Kirchhoff stress tensor equals the variation of Green-Lagrange strain tensor inner product with the second pure Kirchhoff stress tensor. These are so-called power conjugates to each other, which means that their inner products express the internal power of this body. And this is an additional reason why we use S and E as pairs to construct our constitutive law. So after we established this equation, we can then rewrite our weak form as variation of E inner product with second pure Kirchhoff stress tensor. This would represent our internal virtual work, and then equals to the external virtual work done by the body force and surface tractions. So I would like to remind you of the weak form or principal virtual work that we've used in linear finite element method. So try to connect the two and compare the differences. In linear FE, everything is defined in the current deformed configuration, although we never need to worry about it because we always eventually integrate on the original domain. But in fact, these are only defined in the current deformed configuration. But now we've defined its equivalent in the initial configuration, which we know of, but with different quantities, right? These are all defined in the initial configuration. So U here is a function of the capital X. We have a Lagrangian description. So to summarize what we've learned in this lecture on geometrical nonlinearities, we've started with the descriptions of kinematics, such as the deformation gradient, the Green-Lagrange strain tensor. We have then moved on to statics and introduced concepts such as first Piola-Kirchhoff stress tensor and the second Piola-Kirchhoff stress tensor. And we've made the connection between S and E, and by saying that they are candidates for each other in terms of forming a constitutive law. In addition, they are power conjugates to each other, which additionally reinforce this construction. We then presented the balance laws, the strong form, also called equilibrium equation, in both the initial and deformed configurations. And then we derived the weak form or principal virtual work for the initial configuration with the Green-Lagrange strain and second Piola-Kirchhoff stress. For next week, what we are going to do is to use finite element method to discretize this weak form. By discretization, I mean that I'm going to replace the U by a shape function matrix n times a degree of freedom vector, and then I replace the variation of E by some strain displacement matrix usually called B times the degree of freedom vector. Okay, so I think in linear FEM you should already come across these terms. Then we're going to obtain the internal force and external force, and then we are going to calculate the tangent stiffness matrix. This is the end of this week's lecture. I hope you are not too lost. I know that it's a bit theoretical, but I have to go through this with you because these are the foundations for geometrical nonlinear FEM.